Welcome guys, my name is Mohamed Yahiya and I'm going to explain the problem, dining philosopher problem. So what a dining philosopher problem is? Imagine a round table with 5 philosophers, P1, P2, P3, P4 and P5 with 5 forks, fork F1, F2, F3, F4 and F5. So each of them has their food. So what the problem is, each of the philosopher need 2 forks to eat. So they have only the 5 forks totally on the table. So imagine P1 takes the 2 forks, F1 and F2. So what the problem is, he starts to eat while the philosopher P2 have only the fork F3. Now imagine P3 takes the fork F3 and F4. So P3 takes the fork F3 and F4. So now P3 starts eating. So who are the people waiting? P2, P4 and P5. So this is what the dining philosopher problem is. So what is the basic workaround is? That will be on my slide. A zero code which generally implements the workaround, the basic workaround of the dining philosopher problem. Let me write a simple code. First, thinking state, and then the philosopher take fork. I is the ID of the fork. Take fork. I plus 1 mod 5. So then after taking the fork, he will be obviously going to eat state. So eat. After eating, he releases his fork. So put fork I and put fork I plus 1 mod 5. So imagine that the philosopher P1 takes the fork F1. So what will be his next fork could be taken is 1 plus 1 mod 5 is obviously equals 2. So he will be taking the fork F2. Now after taking both the fork, he will enter into eating state, and after eating he puts the fork 1 and 2. Now imagine this case that all the philosopher starts to take the fork simultaneously. Now the case 2 in which the philosopher P1 takes the fork F1, but unfortunately P2 takes the fork F2 and F3. Now unless the philosopher 2 releases the fork F2, P1 couldn't eat his fork. So the workaround for this case could be semaphores. Semaphores is nothing but substituting all the fork variables into an array, say S of I. Now the S of I is something like its range is up to the n number of philosophers present on the table. Say n equals 5 in this case. Now S of I. Now the basic code will change in the form as of the second slide, which I'm going to display. So the second slide suggests thinking of wait and take the fork. S of I. Wait, take fork, S of I plus 1 mod 5. And he enters the end state, sorry, not end, he enters the eat state, and then he signals that he released his fork, which is put fork S of I and signal put fork S of I plus 1 mod 5. I mean, this 5 is nothing but the value of n. So S of I. Totally semaphores are S1, S2, S3, S4 and S5. Now all these, all these semaphores are initialized with the value 0, because 0 means all the forks are now in released state. So all the semaphores, all the forks are in release state now. So as per the condition, the philosopher P1 takes the fork S1 and S2, and P2 takes S2 and S3, P3 takes S3 and S4, P4 takes S4 and S5, followed by P5 takes S5 and S0. Now imagine that P1 takes the fork S1 and S2. Now it is changed to 1 because the fork has been taken. Because both the fork has been taken now, P1 is entering into the critical state, which is the eat state. Now already the S2 value is 1 and P2 could be blocked because of both the fork are engaged to philosopher 1. So P2 could be blocked because both the forks are engaged to philosopher 1. Now this state is blocked now. Now let me come to the philosopher 3. He takes the fork S3 and S4. So this will become 1, 1. Now this was taken. Obviously, now the P4 will be on the blocked state because the fork 4 was taken by P3. P4 couldn't eat, right? So he is also in blocked state. Now P5 takes the fork S5. Also, he enters into the the blocked state because he doesn't have the another fork in his hand, right? So he is also entering into the blocked state. Now the P1 and P3 are eating while P2, P4 and P5 are waiting. Now the philosophers plan a strategy. Let's say again the S1, S2, S3, S4 and S5 was initialized to 0. It is in release state now. Initially P1 takes the fork S1 and now P1 asks P2 to take his left side of fork. Before that, this fork S1 is the left side fork of philosopher 1. Now philosopher 1 asks the philosopher 2 to take his left hand side fork. So P2 will be engaged with the semaphore S2, followed by P3 will be engaged with S3, P4 will be engaged with S4 and P5 will be engaged with S5. S5, yes. Now, each of them has a fork on their left hand side. This is distributed on the pattern of circular way. Now, each of the philosopher has one fork on their left hand. What the state will now occur is five of the philosopher couldn't eat at all. This state is defined as deadlock. Now, to release the deadlock, let me plan a strategy. Now, as per the condition, the basic condition, P1 have to take the fork S1 and S2, right? Followed by P2, S2 and S3. P3, S3 and S4, S4 and S5, S5 and S1. Now, the philosopher 5 stubbornly wants to take his right hand side fork first, followed by the left hand side fork. So, the pattern changes over here. S1 and S5. So, S1 takes the fork, the philosopher 1 takes the fork S1. So, 1. The next philosopher takes the fork S2, which is obviously his left hand side fork, followed by S3 and S4. Now, for the philosopher 5, only the left hand side fork, which is F1, could be, the left hand side fork, which is F5, will be available. Now, obviously, the philosopher 5 has to take his right hand side fork, but unfortunately, he doesn't have the right hand fork available because this fork is being engaged to the philosopher 1. So, he leaves the left hand side fork as it is. Now, what the advantage of the philosopher P4 is, now he takes the fork F5 and he has two forks right now. So, after getting his two forks, he will be entering into the eating state. Now, these forks F4 and F5 will be engaged to philosopher 4. Now he finishes eating and see, he taken the fork F5, right? So 1 and 1. Now he starts eating and he finished eating. Philosopher 4 left the table and the fork F4 and F5 is released now. The philosopher 4 gets out of the table now. Again, the forks were released. Again, 0, 0. Maybe like this. 0 and 0. Now again, P3 has the F4 available now. So, P3 tries to engage with the fork F4 and F3. Now he enters into the eating state and he got the fork S4, so it is 1. So after eating, he again releases the fork, which leads to the state of 0 and 0. Now P3 has eaten and leaves the table. Now for the case of P2, he has the fork S3 available now and he takes the fork S3. So he taken the fork. Now the state of S3 became 1. Now he engages with these two forks and eating, and after eating, P2 leaves the table. Now P2 finished eating. So again the state gone into 0. So now P1 has the fork F2 available, so he takes the fork S2, so 1 1. Now he enters into the eating state, followed by releasing both the forks. Now P1 leaves the table, so again 0 and 0. Now P1 has completed eating. So who else is waiting? P5. He has to finish his food yet, right? So P2 has now now P2 has his right hand side fork, which is S1, and his left hand side fork S5. So he engages both the forks and enters into the eating state. After that, he releasing both the forks. So P5 completed eating. This is the total workaround of the dining philosopher problem. So now for any number of philosophers on the table, the n-1 philosophers should follow a certain order, where the nth philosopher must follow the reverse order. So the final workaround of this code will be as the final slide. So thank you guys. This is about the dining philosopher problem and its solution.